let's do this again. So now we're going to just do a lecture on hemostasis. Hemo meaning blood, stasis meaning to stabilize or maintain. So hemostasis tells us that we're maintaining our blood, and we need to do this all the time. Actually, we're stopping bleeding. So if there's any sort of vascular damage, the body needs to fix that. It's normal homeostasis. Again, it's occurring all the time. So let's go through it. If there is damage to the blood vessel, we need to create a clot, and that's going to allow the body time to fix that blood vessel. There are 3 phases to hemostasis. There is vascular spasm, platelet plug formation, and coagulation. So right after an injury, however that injury occurs, whether it's just weakening of the wall or whatever the case may be, this blood vessel is going to spasm and it's going to constrict. It's going to shrinky-dink down, and when it shrinky-dinks down, well, it's a smaller tube and less blood can flow through it. And therefore, we don't lose blood out into the system, out into the tissues and stuff, because vascular spasm. So it's the very first response. It's not going to last very long. Okay, it's not going to last very long. So we need to make sure that we patch the hole, so that when the vascular spasm goes away, we don't just lose blood out of that hole anyways. So what happens? The next step is a little bit trickier. Those thrombocytes are going to start to stick to the wounded site. And when they stick, they become even stickier, and they start to accumulate more and more thrombocytes to that site. My dog's going crazy. Okay, yeah, but we're not done yet, because there's still a lot of blood flow past this wounded site. And right now, all we got is a bunch of debris in the back of the truck. You ever seen those trucks driving down the road and they got tons of stuff in them, and you're like, "Ooh, that's gonna fly out." Well, that's what's going on here, right? If we just have platelets in place, sure, they're sticky, but there's a lot of force of blood flowing by this site, and it can just shear that platelet right off. So we need to, just like a with junk back, we need to put a mesh on it. We need to tie it down. And that's the last stage. The actual formation of the blood clot occurs because a fibrin mesh is going to tie this entire platelet plug into place. And that is going to allow the tissues to form around this. It's called coagulation, okay? And it's a pretty important step to this whole mess. But I don't want you to think it ends here. There's actually a 4th step to all of this. Do you want blood clots just hanging out in your blood all the time? Do we want these big balls of fibrin mesh? What if they release? What if they go into your bloodstream? It's going to end up causing strokes and attacks and all sorts of nasty stuff. So the 4th stage, which isn't written here, is we got to break this coagulation, this blood clot down in the end. And we're going to talk about that as well. So step 1, powerful vasoconstriction. The blood vessel is going to constrict, and that is going to disallow, look at how tiny, shrinky-dink down this thing is. That is going to disallow blood from getting through this blood vessel. Doesn't last long, several minutes. So we need something else to come into play to patch that hole. Now, during normal blood vessel life, when there's no damage, that blood vessel, well, it's healthy, it's happy. And platelets are not aggregating. We do not get platelet plugs in a normal, healthy blood vessel. That would be completely counterintuitive. So we can't have that. So healthy cells, healthy epithelial tissue, healthy underlying collagen matrix, these are producing signals that say, we're healthy. No platelets should come here. We're healthy. What are those signals? Those signals are right here. It's called prostacyclin and nitric oxide. Both of these are important, and both of these I can test you on pretty easily. Prostacyclin and nitric oxide. I'm going to have a slide that describes each one in more detail in a little bit. But these are local factors released from these tissues that say, hey, we're healthy, we're happy, don't come by. We don't want you here. You're not welcome. Nitric oxide has another function. Please write this down. Nitric oxide is also a potent local vasodilator. So it's going to cause that blood vessel not to shrinky dink, right? There is no vascular spasm because of the presence of nitric oxide in healthy tissue. Nitric oxide is a vasodilator. It's going to help with the keeping this blood vessel enlarged. But what happens in injury? So in injury, remember, these are healthy cells producing prostacyclin and nitric oxide. Well, shoot, now they're injured. And if they're injured, are they still secreting prostacyclic and nitric oxide? No, they're damaged. They're gone. They're not there anymore. Does that make sense? And if those cells are damaged, then the collagen matrix that helps to find the outside of most of the organs of the body are made of collagen, right? Well, this collagen matrix becomes exposed, whether it's cut all the way through or scraped or whatever. It doesn't really matter. What's going to end up happening is that the tissue that has been injured, one, stops prostacyclin, stops nitric oxide release. Therefore, platelets can start to aggregate. They're adhering to this area because there's no prostacyclin, because there's no nitric oxide. And as those platelets begin to adhere, they become active. Again, as those platelets begin to adhere, they become active. A little bit more going on here. I'll just go through it in just a second. So the loss of prostacyclin, the loss of nitric oxide, the platelets to start to become active, and they adhere to the site of the injury. And as they do that, the platelets start to change their shape from a nice round shape to a much more, well, jagged-edged shape. Nice, smooth, round. They don't stick to one another. Versus a edge shape, they become very, very sticky. So as platelets become activated, they become very, very sticky. And a thrombocyte binds to a thrombocyte at this point. Platelet aggregation. In addition, these activated platelets start to produce a couple of other factors. One of the main ones you guys need to know about is called thromboxane A2. Thromboxane A2. And thromboxane A2 is like a little signal that says, all right, more platelets, come here. Hey, platelets, come over this way. And so those platelets are going to be attracted to this area, become active, and produce even more thromboxane A2. In addition, they produce ADP. As normal healthy tissue produces AMP. And this ADP is important in the platelet aggregation process, but I tend not to test you guys on it. The last thing that's on this slide that's really cool is the von Willebrand factor. Von Willebrand factor. Von Willebrand factor is produced by normal collagen, and during injury, the von Willebrand factor will be exposed, and that is something that helps platelets adhere. But there is a disorder, a mutation. Some people don't have the von Willebrand factor. And if they don't have the von Willebrand factor, then that damaged tissue doesn't allow platelets to adhere as well. So those patients have a bleeding disorder because of the loss of the von Willebrand. If platelets don't adhere, they don't become active. They don't become active. They don't produce thromboxane A2. They don't produce thromboxane A2 and ADP. Then more platelets aren't attracted to that area, and the platelet plug doesn't form. Crazy. The platelet plug is forming because of the site of injury, These normal healthy cells are no longer producing prostacyclin. They're not producing nitric oxide. Therefore, this tissue has exposed von Willebrands, and these platelets start to be attracted to that area. As they are attracted, they produce thromboxane A2 and ADP, and that's going to start to activate even more platelets to come to this area, and it keeps building up and building up and building. And it ends up producing this platelet plug. There's a little bit of fibrin mesh on here, but this is caught early enough that mostly what we have here are just platelets, sticky platelets that are adhered to one another. This is surface electron microscopy. It's just gorgeous. Really cool picture. So what else is going on with these platelets, these activated sticky platelets? They also produce some other things like serotonin. You've already seen thromboxane A2. So what sort of functions does serotonin and thromboxane A2 have other than what you guys already learned about thromboxane A2? Well, it prolongs that vascular spasm. So instead of only lasting a couple of minutes, it can last 5 minutes. Good, awesome, we're not bleeding out. ADP and thromboxane A2, this is activating other platelets. It's a positive feedback loop. Last but not least is PF3. PF3 is enhancing the blood clotting at the local area. You haven't seen it in any of the diagrams, so I'm probably not going to test you guys on it thoroughly. Again, just this is a summary slide. So what do we know about healthy endothelial tissue? Is it's producing prostacyclin and nitric oxide. And will platelets adhere? No, right? They're healthy. So platelets would just go on by. But what about in the tissue that becomes damaged? At this exposed site, there's von Willebrand's factor, and that's going to start to cause these platelets to be attracted to this area. And when they are, a couple of platelets will activate, and those platelets will start to produce ADP and thromboxane A2, and they will activate even more platelets. It's a positive feedback. It's going to keep on happening, keep on happening, keep on happening. It's a big loop. Until when? Well, until it gets meshed, but then again, until that tissue gets healed, right? Once that tissue is healed or in the surrounding area, boom, again, prostacyclin, nitric oxide, the von Willebrand's factor has now been covered up again, and platelets won't adhere. Pretty cool. But we're not done, because we're driving down the road with a truck that doesn't have all the materials tied down. So we need to tie this down, and that's through a process called coagulation. Okay, coagulation is taking those platelets and that platelet plug and creating a fibrin mesh around it. And it requires so many crazy things. The list of factors required for coagulation is astronomical. And the reason why is because we do not want coagulation to occur when we do not want coagulation to occur. So we have all sorts of checks and balances in the body to help prevent abnormal clotting. So what do we require? You need to know this list in essence. You need clotting factors. We're going to learn about some of these clotting factors, but they are proteins like fibrinogen and plasminogen. Are 90%, greater than 90% plasma proteins produced from, always the bridesmaid, never the bride, good old liver. What else do we need? Platelets. And what else do we need? Calcium. Calcium is important for so many things in your body. And vitamin K. This is a very unique vitamin, vitamin K. Vitamin K is a very difficult vitamin to get from your fat. Your bacteria in your large intestines are what allow us to digest vitamin K. You have no ability to digest vitamin K in and of yourself. You need your bacteria in your large intestines to do the job for you. Dun dun. Vitamin K. Vitamin K is essential for all sorts of clotting factors, which I won't make you guys too accountable for. You need to know this basic list. Clotting factors like fibrinogen. You'll see that in a following slide. Platelets, calcium, and vitamin K. You must know all of that. What's essential for coagulation? Boom, 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 and a boom. There are ways to look at this through different flow charts because coagulation, again, requires multiple steps. There's an intrinsic within, inside, and an extrinsic from outside. There are two different pathways for coagulation that must proceed along both pathways for coagulation to properly occur. If just the intrinsic pathway is activated, you won't get the final coagulation step. If just the extrinsic pathway is activated, get the final coagulation step. You need intrinsic if there's damage to the inside of the blood vessel, extrinsic if there's damage to the outside of the blood vessel. Intrinsic, that's all about the platelets. It's all about that base. It's all about the platelets, and this is going to take some time for the platelets to aggregate. From inside now, extrinsic, what we're actually talking about is the collagen matrix. We're talking about damaged tissue, the collagen tissue. So if there is damage to tissue outside of the blood vessel, including the interstitial fluid area out here, outside, then that's going to trigger the extrinsic pathway. Again, you need both intrinsic and extrinsic. There's a crazy flow chart that goes into play here, huh? You don't need to know all of this. Promise. Class. You can always look this up later. But each one of these factors is required for coagulation. You got to have factor 12, factor 11, factor 9, factor 8. Whew. Factor 8 over here, tissue factor 3 over here. You need calcium, platelet factor 3, platelets themselves. Need checks and balances to make sure that clotting only occurs when we want it to clot. Once the extrinsic and intrinsic pathways have both done their tang, the common pathways up. And this is where the fibrin mesh comes into play, and this is what you guys need to know. So you guys need to know the common pathway. The common pathway, again, is all about extrinsic and intrinsic factors working together. So extrinsic, this is intrinsic, platelets, PF3, and then you end up making it down to the common pathway, which is found down here. And the portion of the common pathway that you guys are required to understand from is prothrombin. Prothrombin. This is the beginning of the pathway you guys are required to understand, other than understanding that calcium is very important in most of these processes. And vitamin K is important in producing most of these other factors. So that's how important vitamin K is. So low calcium levels or low vitamin K levels, these cascades aren't going to work. Coagulation doesn't properly occur and your patient bleeds out and dies. Is not good. So let's get down to the common pathway part you guys need to understand is that there is a prothrombin out in your bloodstream. There's also a prothrombin activator already in your bloodstream. And there's something called fibrinogen already in your bloodstream. They're all just hanging around there and they're waiting for pathways to activate them. Prothrombin. The pro just glitched, but I think I'm okay. The pro on a protein name, prothrombin, tells us that thrombin is inactive. As long as the pro is attached, then this protein is inactive. So what needs to happen is something's going to come into play. A prothrombin activator going to cleave the pro off of the prothrombin. And what are you going to be left with? Thrombin. Thrombin is a protein that can go through your system and it's going to activate another protein called fibrinogen. Just like pro, ogen, if it's in the word for a protein, ogen tells us that it's inactive. So fibrinogen means that we have an inactive fibrin. So just like prothrombin, pro tells us it's an inactive thrombin. Well, now we got fibrinogen, we have an inactive fibrin. The function of thrombin is to cleave the OG off of fibrinogen, so we're left with fibrin. And fibrin is the final protein activator that ends up producing the fibrin polymer, the mesh that ends up creating this, cool net-like network over the top of that platelet plug. Factor 13, calcium is required for that step right there too. So that's what we have in this flow chart. Check it out. I got prothrombin. Prothrombin is going to be activated by a pro activator, and as we activate it, the pro gets cleaved off, and what are we left with? Thrombin. It has many functions. Positive feedback loop to continue to activate prothrombin. Thrombin also acts back on the platelets and helps with their aggregation. Thrombin activates the factor 13 required for fibrin. And last but not least, the one that you guys need to know for the exam, for sure, is that thrombin activates fibrinogen. It's going to cleave the ogen off of fibrinogen. What are you going to be left with? Fibrin. And then that fibrin gets stabilized into a mesh network. And now we have this fibrin mesh. Well, we're not done yet. Of course we're not done yet, because once the wound is healed, we need to get rid of this fibrin mesh. Otherwise, you're stuck with a clot in your bloodstream, and it's not good. Then it breaks off and it ends up in your heart, and then it gets shot out of your heart into your brain, causing strokes and emboli and all sorts of nasty things. So we need to get rid of that clot. It's a really important part of this process. You got to get rid of that clot. And the first thing that's going to happen is the fibrin mesh is going to shrink. And as that happens, the platelet aggregation and stuff is going to start to drop off, but we still got this mesh of collagen. We need to get rid of that. And the way we get rid of that is through another protein produced by, always the bridesmaid, never the bride, produced by the liver, and it's called plasminogen. So what did you just learn about the ogen? It means it's inactive. Have an inactive form of plasmin. Plasmin is able to dissolve fibrin. So once we activate fibrin, we now have something that can dissolve that fibrin. Super cool. So what's going to happen is when that blood clot's been on for a long enough time, it's going to start to secrete what's called TPA. TPA is tissue plasminogen activator. So again, it's got to be around for a couple of days, 2 days or so that the wound starts to heal. Then it starts producing TPA. TPA, exactly what its name would imply, tissue plasminogen activator. It's going to cleave the ogen off of the plasmin. And now we have active plasmin. And as long as we have active plasmin, we start to dissolve that blood clot. There's a lot less checks and balances for plasmin. Basically, you just need to have a clot that's present. The reason why is because getting rid of the clot is really darn important. So we have lots of ways to, I guess not lots of ways, but we have one real simple loop for producing plasmin. Well, as long as the blood clot is present for a long enough period of time, it produces tissue plasminogen activator, which now cleaves the ogen off of plasmin. Boom, we got active plasmin, which dissolves that blood clot. Why is this important? Because of thrombotic events. What is a thrombus or a thrombotic event versus an embolism? Anybody ever wonder that? Maybe? If you ever heard of, a family member that has an emboli versus a thrombic event. Well, a thrombus is when you got clots that start to form around like stiffening valves of the body. So the valves might stiffen up, or the arthrosclerotic stiffening or something like that, and then you end up with blood clotting where it shouldn't clot, and it's not getting dissolved, so it builds up and builds up and builds up. This is called a thrombus. What's real dangerous is when the thrombus gets cleaved off. If there's enough pressure in the system, a piece of the thrombus might shoot off, and that's what goes back to the heart, to the brain, so forth, so on. And this is called an embolism. The actual physical structure here is an embolus, but yeah, that's an embolism. That's it. Go into this lecture, maybe watch some of these videos on Axis. They're extremely helpful. I finally didn't have an internet issue. A lot of internet issues lately, of course. I hope that is helpful, Stasis, and let me know if you guys have any questions. Throw me a text. All right. Adios.